So let us now get started with the topic of AC analysis. So what is this AC analysis? So far, if you recall, all the circuits have been driven by DC sources. We studied first order circuits, we studied second order circuits. Before that, we studied a number of important circuit theorems. But in every circuit, we only had DC sources driving the circuit. Now we are going to look at the same circuits, but they will be driven by AC or sinusoidal sources. Okay. So what is it? Circuits driven by AC or sinusoidal sources. What will the different voltages and currents be in the circuit? That is the agenda of this topic, which is AC analysis. Okay, circuits driven by AC or sinusoidal sources. Well, before that, we have to look at linear systems in general and how linear systems would respond to what? Sinusoidal inputs. So if you have a linear system, okay, so if you have a linear system for which the input is a sinusoidal function. The input is what? A sinusoidal function. So every sinusoidal function will have an amplitude, it will have a frequency and also a phase angle. Yes. So for this linear system, what is the input? It is a sinusoidal. Let it be some Vp sine omega t plus theta. So what is the input for this linear system? Vp sine omega t plus theta. So what is the frequency of the input? It is omega. What is the amplitude of the input? It is Vp. And what is the phase angle of the input? It is some theta. Now the property of any linear system is that any linear system for which the input is what? A sine wave, even the output at steady state will also be a sine wave at the same frequency. This is the most important property of a linear system. If the input is what? Sine wave, and if the system is what? Linear, then its output at steady state is also what? Sine wave at the same frequency. You understood? So here, output at steady state is also a sine wave at the same frequency. Let me make a small modification. Let me denote the frequency of the input sine wave by omega naught. So now what is the input? Vp sine omega naught t plus theta. Okay. Now the output at steady state would also be a sine wave at the same frequency. So what are the only two things that will get modified? Amplitude will get modified, phase angle also will get modified, but not the frequency. So even the output at steady state will be a sinusoid with some amplitude which can be some Vp prime times sine of the same frequency, that is what? Omega naught t plus some other phase angle, let it be phi. Let it be phi. This is the crux of signals and systems. So if you have any linear system and if a sine wave is applied as the input, even the output at steady state would be a sine wave at the same frequency. Okay. So a sine wave goes through the linear system and comes out as what? Sine wave at the same frequency. I'll say it again. A sine wave will go through a linear system and come out as what? The same sine wave at the same frequency. But what will get modified when the sine wave goes through the linear system? Amplitude and phase will get modified. Input side, the amplitude is what? Vp, but the output, the amplitude can be something different. Okay, let it be some Vp prime. Also input side, what is the phase angle of the sine wave? Let it be some theta. Now on the output side, the phase angle can be some other value, maybe some phi. You understood? But look at the frequency of input and the frequency of output, both are what? One and the same. So frequency does not get modified. amplitude and phase will get modified. Okay, I'll just write it. So when a sine wave goes through a linear system, it will come out as what? A sine wave at the same frequency with its amplitude and phase getting modified. Amplitude and phase will get modified. I hope this point is clear. So if you understand this point, then half the job is what done. Output at steady state will also be a sine wave at the same frequency. Now, if you have to talk about a linear circuit, any linear circuit is also what? A linear system, because after all circuits are what? Systems. If the circuit is linear, then the system is also what? Linear. If the circuit is non-linear, then the system is also going to be non-linear. So now let's say we have a linear circuit. We have what? A linear circuit. And let's say this linear circuit is being driven by a sinusoidal source. It can be a sinusoidal voltage source or a sinusoidal current source. Okay. Once again, let the input be what? Some Vp cos omega 1t plus theta 1. So what is the input source driving this linear circuit? It is a sinusoidal voltage source whose expression is what? Some Vp cos omega 1t plus some theta 1. So what is the amplitude of the input voltage? It is Vp. Frequency is what? Omega 1. Angle is what? Theta 1. Okay. Now this linear circuit, after a long time, will it not reach steady state? Any circuit, if you give it sufficient time, it will reach what? Steady state. And when the linear circuit reaches what? Steady state, every voltage and every current. This is very important. If the linear circuit reaches steady state, ideally, when will any circuit reach steady state? It will reach steady state at t equal to what? Infinity. So at t equal to infinity, when our linear circuit reaches what? Steady state, every voltage and every current in that linear circuit will also be a sinusoidal function at the same frequency as that of the input sinusoidal source. What is the frequency of the input sinusoidal source? It is omega 1. So if this linear circuit reaches what? Steady state, every voltage and every current in that circuit is also going to be sinusoidal at the same frequency. What is that frequency? Omega 1. So what should I write here? Every voltage and every current at steady state is also going to be sinusoidal at the same frequency. Every voltage and every current at steady state is also going to be sinusoidal at the same frequency. This is the property of any linear circuit. Now you already know how to identify whether the given circuit is what? Linear or non-linear. For any circuit to be linear, it should consist only of linear circuit elements. Now what are these various linear circuit elements? Mainly we have what? Resistors, capacitors and inductors. And apart from these three passive components, we also have linear dependent sources. What is it? Linear dependent sources. So resistors, capacitors, inductors and linear dependent sources. If these elements are present in the circuit, then the circuit is said to be linear. Then this is going to be valid. At steady state, every voltage and every current will also be sinusoidal at the same frequency. What will get modified? Amplitude and phase angle will get modified. I hope this part is clear. Okay. Of course, before reaching steady state, whatever the circuit will do, that is called as what? The transient response. And you know the nature of the transient response, it only depends on the nature of the circuit but not the input source. So if it's an RC circuit, if it is an RC circuit, you know the natural response is going to be the form some A times e power minus t by tau. And if it's an RLC circuit, again the natural response will be what? Either over-damped or under-damped or even critically damped. And to that natural response, you should add the steady state response to get the complete response. But in this topic, we will be only interested in the steady state response and not the complete response. That means what? All our circuits driven by various sinusoidal current and voltage sources are always assumed to reach what? Steady state. So it is always assumed that our linear circuit has reached what? Steady state, in which case, you know, at steady state, the transient or the natural response will completely decay to zero, so that the only thing that is left is what? The steady state response. So the complete response at steady state will simply be equal to what? The steady state response. And the steady state response of any linear circuit to a sinusoidal input is also going to be sinusoidal at the same frequency. Okay, that's the point. Steady state response of any linear circuit to a sinusoidal input is also going to be sinusoidal at the same frequency. Steady state response of any linear circuit to a sinusoidal input is also going to be sinusoidal at the same frequency. Okay, that means what? Every voltage and every current is also going to be sinusoidal at the same frequency as that of the input. But every voltage will have its own amplitude and every current will have its own amplitude. Not only that, every voltage and every current will have their own phase angles. But what is same for all the voltages and currents? Frequency is what? Same. Amplitude can be different for different quantities. Even phase angle can be different for different quantities. You understood? This is true for any linear circuit. So what is the bottom line here? So when a sine wave passes through or goes through a linear system, it will come out as what? A sine wave at the same frequency. When a sine wave goes through a linear system, it will come out as what? A sine wave at the same frequency. But this is not true for other inputs. For example, if a square wave passes through a linear system, it will never come out as what? A sine wave. Square wave, sorry. If a square wave passes through a linear system or goes through a linear system, it will never come out as a square wave unless the system has got what? Infinite bandwidth and so on, which is never the case. So square wave, when it goes through a linear system, the output is not exactly square. Even if a triangular waveform goes through a linear system, again the output will not be exactly triangular. So the only input waveform which can go through a linear system and come out with the same shape does not get modified. The only waveform for which the shape of the output is same as the shape of the input is what? The sine wave. That is why sine waves are extremely important in the testing of linear systems. Okay. Anyway, so now that we know that at steady state, by the way, if the circuit is what? Driven by DC sources, even though it's a trivial point, you should know this. So let's say we have a linear circuit for which input is what? DC. For which input is what? DC. Then the output at steady state is also what? DC. And this circuit reaches what steady state? It reaches DC steady state. And you know, at DC steady state, cap becomes open and the inductor becomes what? Short. So when will any circuit reach DC steady state? If the input source is what? DC in nature. But if the same circuit let's say the circuit is what? Linear again, but this time the input is what? Sinusoidal, meaning the input is what? AC. Now the circuit will reach what is called sinusoidal steady state or AC steady state. So DC is steady state when the input is what? DC. Sinusoidal steady state when the input is what? AC. Common sense, okay? So this time the output at steady state is also going to be what? AC at the same frequency. AC at same frequency, and this steady state is called as what? Sinusoidal steady state. So this AC analysis, this topic, is also called as what? Sinusoidal steady state analysis. That is, when the circuit reaches sinusoidal steady state, what are the different voltages and currents going to be? That is the main goal of this, or main objective of this topic. It is to find various voltages and the currents in the circuit when the circuit reaches what? Sinusoidal steady state. So sinusoidal steady state, okay? So clearly at sinusoidal steady state, the transient response will decay to what? 0. So the only part that is left is what? The steady state part, and the steady state part is what? Going to be AC at the same frequency. So let's say we have a sinusoidal voltage which goes as some Vp cos omega t plus theta. We have a sinusoidal voltage which is some Vp cos omega t plus theta. So what is Vp here? It's the amplitude of the voltage, or the sinusoidal voltage. Omega is what? Frequency. Theta is what? The phase angle of the voltage. So all of you know that e power j theta is what? Cos theta plus j sin theta. So what is the real part of e power j theta? It is cos theta. Yes or no? Real part of e power j theta is what? Cos theta. Now coming to this sinusoidal voltage, which is Vp cos omega t plus theta, this can be written as what? Real part of Vp times e power j omega t plus theta. Please convince yourself that this is correct. So the original sinusoidal voltage is what? Vp cos omega t plus theta, but that can be written as a real part of some complex number. By the way, what is this e power j theta? E power j theta, is it not a complex number? Cos theta is what? The real part. Sin theta is what? The imaginary part. Similarly, even the argument of this real part is also what? A complex number. What is that complex number? Vp e power j omega t plus theta. This thing, it is what? A complex number. And our sinusoidal voltage is what? Real part of this complex number. I hope everybody agrees with this, because you know we can write e power j omega t plus theta as what? Cos of omega t plus theta plus j times sin of omega t plus theta. Then if you take only the real part, you will get back the original sinusoidal voltage, which is Vp cos omega t plus theta. Is this clear? Aditya, Dineshwaran, Uday, is it clear or not? Yes. So this Vp cos omega t is what? Real part of this complex number. Now this complex number, what is this complex number? Vp e power j omega t plus theta. This e power j omega t plus theta, I'll write it as, so first we have real part of Vp, I'll write it as Vp itself. this e power j omega t, e power j omega t plus theta, I'll write it as e power j theta times e power j omega t. Can I do so? E power a plus b is what? E power a into e power b. Same thing I did here. E power j omega t plus theta is same as what? E power j theta times e power j omega t. Now inside the argument of the real part, we have what? Vp times e power j theta times e power j omega t. Now what is that multiplying factor of e power j omega t? What is that multiplying factor of e power j omega t? Is it not Vp e power j theta? Inside the argument of the real part, what is the multiplying factor of e power j omega t? It is Vp e power j theta. What kind of number is this Vp e power j theta? Please tell me, this Vp e power j theta, is it a real number or a complex number? Vp e power j theta, which is the multiplying factor of e power j omega t, is it real or complex? Vp e power j theta, is it real or complex? It is complex, because what is e power j theta? Cos theta plus j sin theta, or you can say Vp e power j theta is going to be Vp cos theta plus j Vp sin theta. So this complex number, multiplying this e power j omega t, this complex number is what is called the phasor voltage. This complex number, which is multiplying e power j omega t, this complex number is what we call the phasor voltage. So what is this phasor voltage? It is a complex number which will represent the actual sinusoidal voltage. Phasor voltage, it is what? A complex number which has units of voltage, and this complex number is going to represent, the original sinusoidal voltage. And what is our original sinusoidal voltage? Vp cos omega t plus theta. Now this phasor voltage will be denoted by capital V. You understood? Yes. So here, let's be very clear about notation. From now onwards, for a voltage, if I write like this, usually voltage what? Denoted by V. If I write V this way, yes, then it is what? Voltage as a function of time. That is voltage in time domain. Okay. So this is what? Function of time. Voltage as a function of time. So in other words, this is same as what? V of t. But if I write capital V, it is what? The same voltage in the phasor domain. Same voltage in phasor domain. So capital V is what? Not the actual voltage, but the phasor voltage. Similarly, if I write small I, again this current is what? A function of time. We are representing the current as a function of time. Current as a function of time, is it not same as I of t? Yes or no? Current as a function of time is same as what? I of t. Now the same current, if it is what? Sinusoidal, it will obviously be some Im cos omega t plus theta, like that. Even that sinusoidal current can be represented as a complex number, that is what? As a phasor. Okay. Again, small I is what? Current in time domain, or current as a function of time. The same current in phasor domain will become what? Capital I. So what is capital I? Just like capital V is what? The phasor voltage. Capital I is going to be the phasor current. The same small I in phasor domain will become what? Capital I. The same small v, which is V of t, in phasor domain, it will become what? Capital V. So small I in time domain will become capital I in phasor domain. Small v in time domain will become capital V in phasor domain. So in the phasor domain, all our voltage and currents will be denoted by capital V and capital I respectively. And what kind of number is this phasor? It's a complex number. For example, as you can see here, the phasor voltage capital V, it is equal to what? Vp e power j theta. Vp e power j theta. Okay. Anyway, this capital I, it is what? A phasor voltage. Capital I, it is what? A phasor voltage. You understood? Yes. So what is capital V here? It is Vp e power j theta. Vp e power j theta. So what is the result we have here? If you have a sinusoidal voltage of the form Vp cos omega t plus theta, the same voltage in phasor form will be what? Vp e power j theta. So when you are representing voltages and currents in the phasor domain, in a way we are ignoring what? The frequency of the voltage or the current. Because if you look at the phasor representation of the same voltage, it contains what? Vp and theta. Vp is what? The amplitude. Theta is what? The phase angle. But the phasor representation does not include frequency. Yes. But every phasor will be defined at a particular frequency. And that is the frequency of the sinusoidal voltage or sinusoidal current. So every phasor. So this phasor will be defined at a frequency of omega. This phasor will be defined at a frequency of what? Omega. You understood? Yes. So what is the important result that we have just obtained? If you have a sinusoidal voltage which is of the form Vp cos omega t plus theta, the same voltage in phasor form will be represented as what? Capital V is equal to Vp e power j theta. This Vp e power j theta can also be written as what? Vp angle theta. Yes. Now this Vp angle theta can also be written as what? Vp cos theta plus jVp sin theta. What is the name of this representation? Vp cos theta plus jVp sin theta. Is it not the representation of a complex number in rectangular form? Yes. And what is this Vp angle theta? This is polar form. Yes. So this is very trivial. So this representation is called as what? The polar form representation of the phasor voltage. Whereas this Vp cos theta plus jVp sin theta, where you clearly show, separate the complex number into what? Real part plus j times the imaginary part. This representation, it is called the rectangular form. So what is this polar form? Vp angle theta. Now every complex number will have two things. One is what? Amplitude. The other one is what? Not amplitude, magnitude. Every complex number will have what? Magnitude and a phase angle. So what is this Vp? Is it not the magnitude of the phasor voltage? Vp is what? Magnitude of the phasor voltage. What is this theta? Angle of the phasor voltage. And here magnitude of the phasor voltage is same as what? Amplitude of the actual sinusoidal voltage. Be clear about this. Magnitude of the phasor voltage is same as what? Amplitude of the actual sinusoidal voltage. And theta is what? The angle of the phasor. Every complex number will have a magnitude and an angle. So theta is what? The angle of the phasor voltage. And what is theta actually? It is the phase angle of the actual sinusoidal voltage. You understood? So magnitude of the phasor is same as what? The amplitude of the actual sinusoidal voltage or current. And angle of the phasor is same as what? The phase angle of the actual sinusoidal voltage or current. In the context of circuit analysis, this magnitude of the phasor will be same as what? Amplitude of the actual sinusoidal voltage or current. But in the context of machines and power systems, magnitude of the phasor will be equal to what? The RMS value of the corresponding sinusoidal voltage or current. I'll say it again. In the context of circuit analysis, magnitude of the phasor is same as what? Amplitude of the corresponding sinusoidal voltage or current. But in the context of power systems and machines, magnitude of the phasor is not the amplitude, it is what? The RMS value. Vp cos omega t plus theta, what is the RMS value? Is it not Vp by root 2? So the same voltage in phasor form will be represented as what? Not Vp angle theta, but as Vp by root 2 angle theta. I hope it is clear, okay? So in circuit analysis, whenever the magnitude represents the RMS value of the corresponding sinusoidal voltage or current, I will clearly indicate the same. I will clearly write the phasor voltage is what? 100 angle 30 degrees volts RMS. If I wrote RMS, then it means that 100 is not amplitude, it is what? RMS. But if I simply write 100 angle 30 degrees volts, then that 100 volts is what? The amplitude. If I write 100 angle 30 degrees volts RMS, that 100 is what? RMS value of the corresponding sinusoidal voltage. But if I simply write 100 angle 30 degrees volts and just leave it like that, then that 100 volts is what? The amplitude of the sinusoidal voltage or current. So as we go along, you will become more familiar with these things, okay? So in general, in the context of circuit analysis, this magnitude of the phasor is same as what? The amplitude of the corresponding sinusoidal current or voltage, okay? I hope it is clear up to this point, okay? Okay, this time, let's say we have a sinusoidal current of the form IP sin omega t plus phi. So earlier we had a sinusoidal voltage which was of the form Vp cos omega t plus theta, and the same voltage in phasor domain is represented as what? Vp angle theta. What is it? Vp angle theta. Now let us represent this sinusoidal current in the phasor domain, okay? Again, this IP sin omega t plus phi, it can be written as what? You see, what is sin x? Cos of 90 minus x. Yes or no? Sin x is what? Cos of 90 minus x. So sin x is what? Cos of 90 degrees minus x. So here in this I of t representation, omega t plus phi, let it be x. Then sin x can be written as what? Cos of 90 degrees minus the same thing. So cos of 90 degrees minus omega t minus phi. Yes. And then you know cos of minus x is same as what? Cos of x. Yes or no? Cos of minus x is same as what? Cos of x. So what I can do is the same thing, I can write it as IP cos omega t plus phi minus 90 degrees. IP cos omega t plus phi minus 90 degrees. Again, IP cos alpha. Let us call this entire thing as what? Alpha. IP cos alpha, is it not the real part of IP e power j alpha? Yes or no? If I call this entire thing, entire angle as what? Alpha, then IP cos alpha is same as what? Real part of IP e power j alpha. Yes. So this is same as what? This is same as. So this is same as what? The real part of. This is same as what? The real part of. Tell me. I mean, you can't tell, right? IP e power j omega t plus phi minus 90 degrees. This again can be written as what? Real part of IP e power j omega t e power j phi e power j minus 90 degrees. What is e power j minus 90 degrees? You see, e power j 0 degrees. E power j 0 degrees is what? Cos 0 plus j sin 0. Is it not 1? What is e power j 180 degrees? Is it not cos 180 plus j sin 180? Cos 180 is what? Minus 1. Sin 180 is what? 0. So e power j 0 degrees is what? 1. E power j minus 180 degrees is what? Minus 1. What is e power j 90 degrees? E power j 90 degrees will be what? Cos 90 plus j sin 90. So is it not simply j? And what is e power minus j 90 degrees? It will be minus j. So these are some basic identities. E power j 0 degrees is what? 1. E power j 180 degrees is what? Minus 1. E power j 90 degrees is what? Plus j. And e power j minus 90 degrees is what? Minus j. Now come back to this argument of the real part. What is inside the argument of the real part? Ip e power j omega t times e power j phi times e power j minus 90 degrees. So e power j minus 90 degrees is same as what? E power minus j 90 degrees, which is same as what? Minus j. So this can be again written as what? Real part of. So first I'll write Ip, then I'll write e power j phi, then e power j minus 90 degrees is what? Minus j, and then I will write this e power j omega t. Now what is our phasor thing? So if you go back, how did we get that phasor? First of all, I wrote the voltage as what? Real part of some complex number times e power j omega t, and that complex number multiplying e power j omega t is what? Is our phasor. Okay, so it's Vp e power j theta times e power j omega t. Vp e power j theta is what is going to be the phasor voltage. Okay, so now coming to this current, now also are we not having a complex number that is multiplying this e power j omega t, and this complex number is what is going to be the phasor current. Phasor voltage denoted by capital V, phasor current denoted by capital I. You understood? Yes. So what is the actual sinusoidal current? Ip sin omega t plus phi. And what did we get for the phasor current in the end? Ip e power j phi and then minus j. I'll just write it separately here. So capital I, that is what? The same current in phasor form will be equal to what? Will be equal to, first I'll write minus j, then I'll write Ip, and then e power j phi. E power j phi, is it not same as angle phi? Yes or no? E power j phi can also be written as what? Angle phi. So this can be written as what? Minus j Ip angle phi. That's all. So the sinusoidal current is represented as a sine function. Earlier, the sinusoidal voltage was expressed as a cosine function, Vp cos omega t plus theta, and the corresponding phasor voltage, it was what? Vp angle theta. This time the sinusoidal current is expressed as a sine function, something like Ip sin omega t plus phi, and the same current in phasor form happens to be minus j Ip angle phi. You understood? Yes. Now these are like two very important results which we will be using throughout the sinusoidal steady state analysis. Okay, let me write the two results at one place so that you can compare the difference between the cosine function and sine function. Okay, so first let's say we have a voltage V of t which is expressed as a sine function, cosine function. Let it be Vm cos omega t plus theta. Now the very easy way to write this voltage in phasor form is what? What is Vm? Is it not amplitude? Amplitude in terms of, amplitude in the time domain will become what? Magnitude in the phasor domain, magnitude of complex number. Any doubt? Okay, Uday is asking, sir, in phasor also, should we take only real part of the complex number? No, Uday, To get back the actual sinusoidal voltage, you should multiply the phasor with e power j omega t, and then you should take the real part. Yes, if you multiply the phasor, which is a complex number, with e power j omega t, and then if you take the real part of the product, you will get back the original sinusoidal current or voltage. You cannot simply take the real part of the phasor. Phasor is what? Complex. Let it be complex. You multiply that complex number with e power j omega t, then you take its real part, you will get back the sinusoidal voltage or current in the time domain. Okay. So V of t, if it is what? Vm cos omega t plus theta, then its phasor representation is what? Very simple. First you write Vm, then you simply write angle theta. That's all. Isn't it very simple? Vm cos omega t plus theta, the phasor representation would simply be Vm angle theta. And then let's say we have a sinusoidal current which is expressed as a sine function. Earlier the voltage is expressed as a cosine function. Now let's say the current is what? Expressed as a sine function. Again, let that sinusoidal current be some Im sine omega t plus phi. Im sine omega t plus phi. So what is the same current in phasor form? First of all, small I will become what? Capital I. Now also what you should do, just like for the previous voltage, we simply wrote Vm angle theta. Now also you write Im angle phi. Im angle phi. But since it is what? Sine, you just add a additional factor which is what? Minus j. That's all. Isn't it easy to remember? Please note down these two results. Please note down these two results. These are the most important results. If you know these two things properly, then you can solve any problem related to circuit analysis at AC steady state. Okay. So for Vm cos omega t plus theta, the phasor representation is what? Vm angle theta. And for Im sine omega t plus phi, the phasor representation is what? First you write Im angle phi. Since it is sine, you add additional multiplying factor which is what? Minus j. If it is cosine, you just leave it like that, Vm angle theta. If it is sine, you add this minus j. So whether it is sine or cosine, immediately you write amplitude followed by the phase angle, like what? Vm angle theta or Im angle phi. Now depending on whether the quantity is expressed in terms of what? Sine function or cosine function. If it is sine, you add this minus j. If it is cosine, you just leave it like that. You understood? Yes. So just by keeping these two results in mind, you can convert any current or any voltage from time domain into what? The phasor domain. You understood? Yes. Now just to get used to this phasor representation of voltages and currents, let us convert a few voltages and currents from time domain to phasor domain. Okay. Well, before that, this phasor is what? A complex number. Phasor is what? A complex number. And any complex number can be represented on the complex plane. Yes, or any complex number can obviously be represented on a complex plane. So let's say we have first of all we have the complex plane. This is what? The complex plane. You can see there are two axes. This is what? The imaginary part of the complex number. This is what? The real part. So what is this axis? Positive real axis. This is what? The negative real axis. This is what? Positive imaginary axis. This is what? Negative imaginary axis. First quadrant, second quadrant, third quadrant, fourth quadrant. So in the first quadrant, real part, imaginary part, both are positive. In the second quadrant, real part is what? Negative, imaginary part is what? Positive. In the third quadrant, real and imaginary parts both are negative. In the fourth quadrant, real part is positive, imaginary part is what? Negative. Again, extremely obvious. So this is what plane? This is the complex plane. Real axis, imaginary axis. Now, let's say we have a sinusoidal, we have a phasor voltage V1 which is some 5 at an angle 30 degrees. We have a phasor voltage which is 5 angle 30 degrees. Whenever I say phasor voltage, I should also write the units. Phasor voltage will be in units of what? Volts. Phasor current will be in the units of amperes. Okay. If I write volts followed by RMS, if I write 5 angle 30 degrees volts RMS, then that 5 volts is what? The RMS value of the voltage. But if I simply write 5 angle 30 degrees volts, then this 5 volts is what? The amplitude of the sinusoidal voltage. Okay. So here no RMS. So it is understood that this 5 volts is what? The amplitude. Of course 30 degrees is what? The phase angle of the sinusoidal voltage. Okay. Now every phasor is like a vector. Every phasor can be shown as a vector on the complex plane. Every phasor can be shown as a vector on the complex plane. Now every vector will have a length. Every vector will have a length, and every phasor will have a magnitude. Yes. So what is the magnitude? This 5, it is what? The magnitude. Yes or no? And this 30 degrees, it is what? The angle. Magnitude is what? 5. Angle is what? 30 degrees. Now this magnitude, it is same as what? The length of the phasor. You understood? Magnitude of the phasor, in this case, the magnitude is what? 5. So that 5 is also going to be what? The length of the phasor. And this angle of the phasor is same as what? Angle of the phasor with respect to positive real axis. Let me write this properly. So what is this 30 degrees? It is the angle of the phasor, which is what? A vector, with respect to positive real axis in the anti-clockwise direction. Okay. This 30 degrees is what? Angle of the phasor with respect to positive real axis. Positive real axis in the anti-clockwise direction. So a couple of simple but important points. Every phasor can be shown as a vector. Every phasor can be shown as what? A vector on the complex plane. And then every vector will have what? A length, and will also have an angle with respect to what? The positive real axis. Okay. So in this case, what is the length of the phasor or the length of the vector? It is 5 units. It is what? 5 units. What is the angle of the phasor or the vector with respect to positive real axis? With respect to what? Positive real axis. In what direction? In the anti-clockwise direction. The angle is what? 30 degrees. Yes. So will it not be something like this? So this is the representation of the phasor voltage V1. So what is the length of the vector or this phasor? The length is what? 5 units. The angle of this with respect to positive real axis, it is how much? It is 30 degrees. It is what? 30 degrees. You understood? Yes. If the angle is between 90 and 180, the phasor will lie in what? The second quadrant. If the angle is what? In between 180 and 270, the phasor will lie in what? The third quadrant. If the angle is between 270 and 360 degrees, then the phasor will lie in what? The fourth quadrant. Now 30 degrees is what? Positive. 30 degrees is what? Positive. So the phasor should be rotated with respect to positive real axis by an angle of 30 degrees in anti-clockwise direction. Had the angle been, let's say there is one more, let us say there is one more phasor voltage V2 which is also having a magnitude of 5, this thing 5 units or 5 volts at an angle minus 120 degrees. So look at the second phasor voltage V2, which is 5 at an angle minus 120 degrees. So what is the length of the vector or the phasor? Length is always equal to what? Magnitude, which is what? 5. What is the length of V1? 5. What is the length of V2? It is also 5. That means V1 and V2 will have the same length. V1 and V2 will have the same length. But what is different for the two phasors? Angle is what different? Angle of V1 is what? Plus 30 degrees. Angle of V2 is what? Minus 120 degrees. So whenever the angle is what? Negative, the phasor should be rotated from the positive real axis by an angle of 120 degrees in the clockwise direction. If the angle is what? Plus 30 degrees, starting from positive real axis, you rotate it by 30 degrees in anti-clockwise direction. If the angle is what? Plus 30 degrees, like in the previous case, first you get aligned with the positive real axis. Now the angle is what? Plus 30 degrees previously. Then from positive real axis, you should rotate by 30 degrees in the anti-clockwise direction. Now the angle is what? Minus 120 degrees. Again, you initially get aligned with positive real axis. Now once you get aligned with the positive real axis, then you should rotate by 120 degrees, but not in anti-clockwise, but in clockwise, since the angle is what? Negative. Is it clear? So if the angle is what? Positive, rotate in anti-clockwise direction. If the angle is what? Negative, you should rotate it in the clockwise direction. You understood? So first you are aligned with the positive real axis, then you should rotate by 120 degrees in the clockwise direction. So tell me, in which quadrant will the phasor lie in? If the angle is minus 120 degrees, will it not lie in third quadrant? Yes or no? Starting from positive real axis, if you rotate by 120 degrees in the clockwise direction. Why clockwise? Because the angle is what? Negative. Had the angle been positive, then you should rotate in anti-clockwise direction. Whenever the angle is what? Negative, you should rotate in clockwise direction. So from this thing, you should rotate by 120 degrees in the clockwise direction. So this is going to be V2. You can see this phasor V2 and this phasor V1 both have the same length, because magnitude of V1 is what? 5. Magnitude of V2 is also what? 5. Okay. But this angle, what is this angle going to be? Minus 120 degrees. You understood? Yes. So this is how you represent phasors on the complex plane. This is how you represent phasors on the complex plane. Okay. So if the angle is what? Positive, you should rotate in the anti-clockwise direction. And if the angle is what? Negative, you should rotate in clockwise direction. Okay. So once again, let's say we have a phasor voltage V1, which is some 5 angle 30 degrees volts. So 5 is what? The magnitude of the phasor, which is same as what? The length of the phasor. And the angle is what? 30 degrees, which is positive. So from positive real axis, you should rotate by 30 degrees in the anti-clockwise direction. So clearly the phasor would lie in, the first quadrant, and it has a length of 5 units. Okay. So given that this is what? The phasor V1. Let's say we have one more voltage V2, which is 2V1 at an angle 100 degrees volts. So what is V2? 2V1 at an angle 100 degrees volts. You understood? Yes. If V2 is what? 2V1 at an angle 100 degrees volts. First of all, mod V2. What is this mod V2? magnitude of phasor voltage V2. What is the right hand side magnitude? Is it not 2 times mod V1? Yes or no? 2 times mod V1. Because angle 100 degrees. Angle 100 degrees means what? Cos 100 degrees plus j sin 100 degrees. Cos theta plus j sin theta. Magnitude is what? Square root of cos square theta plus sin square theta, which is what? 1. So always angle theta, the magnitude is what? 1. So if V2 is what? Some other phasor voltage, and if it is related to V1 like this, 2V1 at an angle 100 degrees, then magnitude of V2, is it not 2 times mod of V1? That means this V2 phasor, it will be 2 times longer than, it will be 2 times longer than V1. Already V1 is how many units long? 5 units long. So V2, would it not be 10 units long? So the phasor, it will become double in length. Then what about angle? Say from here, we can write angle of V2 is equal to what? Angle of V1 plus 100 degrees. Do you agree with that? Angle of V2 is same as what? Angle of V1 plus 100 degrees. You understood? So what is the angle of V1? Already V1 is what? 5 angle 30 degrees. So angle of V1 is what? 30 degrees. 30 degrees plus 100 degrees. Is it not 130 degrees? So what is the angle of the new phasor voltage V2? It is 130 degrees. Anyway, we already have V1, right? V2 is what? 2V1 at an angle 100 degrees. So what you should do is, first of all, V2 is what? 2 times longer than V1. That means what? V1 will become twice its length. And then V2 is what? 2V1 angle 100 degrees. So V1 should be rotated further by an angle of 100 degrees in clockwise or anti-clockwise. Look at the angle, it is plus 100 degrees. So V1 should be rotated by 100 degrees in the anti-clockwise direction. Then you double the length of V1, you will get what? V2. Is that clear or not? V2 is what? 2V1 angle 100 degrees. Rotate V1 by 100 degrees in the anti-clockwise direction. Then you double the length of V1, you will get what? V2. Already V1 is at an angle of 30 degrees with respect to what? Positive real axis. If you rotate V1 by a further angle of 100 degrees, the net angle, will it not become 130 degrees like we wrote here? Angle 130 degrees, does it not lie in the second quadrant? And its length will be how many units? 10 units. This length is what? 5 units. V2 length, it would be 10 units. 130 degrees. So it will be like this. Okay. That's all. And the new angle, it would be 130 degrees. You understood? Yes. And also here, if you look at this, angle of V2 is what? Angle of V1 plus 100 degrees. This can be written as what? Angle of V2 minus angle of V1 is what? 100 degrees. So phase angle of V2 minus phase angle of V1 is what? 100 degrees. From this we can say V2 leads V1 by 100 degrees. Yes or no? V2 leads V1 by 100 degrees. V2 leads V1 by 100 degrees. V2 leading V1 by 100 degrees is same as what? V1 lagging V2 by 100 degrees. This is again same as what? V1 lags V2 by 100 degrees. You understood? Yes. So if you have the phasor, by the way, this diagram is called as what? The phasor diagram. If you are representing different phasors on the complex plane, then the diagram is called as what? Phasor diagram. And remember, in the phasor diagram, whatever phasors you represent, in the same phasor diagram, you can represent different phasor voltages and phasor currents. All the phasors will be defined at same frequency. You cannot have a phasor diagram where different phasors are defined at different frequencies. You understood? So in a single phasor diagram, all phasors will be defined at one single frequency. So in a phasor diagram, right now in the phasor diagram we have our two phasors, V1 and V2. Because both phasors are present in the same diagram, V1 and V2 are definitely going to be at same frequency. If they are not at same frequency, do not represent them in the same diagram. You understood? So only that set of phasors which are at the same frequency can be represented on the complex plane to get the phasor diagram. You understood? Yes. So here, rotate V1 by 100 degrees, then double the length of V1, you will get what? V2. And V2 leads V1 by 100 degrees. So this 100 degrees, is it not the angle between V2 and V1? Angle of V2 minus angle of V1. That is why it is the phase difference between V2 and V1. So what is the phase difference between V2 and V1? It is plus 100 degrees, which means what? V2 leads V1 by 100 degrees. The same thing can also be said as what? V1 lags V2 by 100 degrees. You understood? Yes. Now I told you what? These phasors are like vectors. Phasors are like vectors. Now there are some laws of vector addition. Some of those things can be applied to what? Phasors as well. Okay. Not everything, but to some extent, whatever results we have for vectors, they can be applied to phasors as well. Once again, let's say this is what? The complex plane. Obviously this is what? The imaginary axis. This is what? The real axis. Imaginary axis, real axis. Let's say we have two phasors. One phasor is what? V1. Another phasor is what? V2. And let the angle between the two phasors be some theta. Let theta be the angle between the two phasors. Okay. Now I would like to find mod V1 plus V2. So when you add the two phasors, how do you add the two phasors? It is similar to what? Adding vectors. You know, I mean, you must be remembering parallelogram, you know, law of addition for vectors. So how do you add these two phasors? It is like adding the two vectors V1 and V2. So the way to do it, you know, you keep one phasor fixed. By the way, all phasors will start from origin. All phasors will start from origin, and this is called the tip of the phasor. This end is called the tip of phasor V1. This is called as what? Tip of phasor V2. Okay. So let's say V1 phasor is what? Kept fixed or constant. Then V2 you translate it such that V2 is what? Shifted to the tip of V1. That is how you add vectors. Okay. So without altering the angle, you know, let this be V2, and then you join the origin and the tip of V2. Yes. So this is what? V1 plus V2. You understood? It is, I mean, this is how you add what? Vectors. Okay. Now look at this yellow color phasor, which is V1 plus V2. Now every phasor will have what? A magnitude. Every phasor will have a length or magnitude. So this mod V1 plus V2 is what? The magnitude of this yellow color phasor, or length of the yellow color phasor. Remember, magnitude in phasor domain is same as what? Amplitude in time domain. Magnitude in phasor domain is same as what? Amplitude in time domain. Okay. Anyway, so how do you find the magnitude of the resultant vector or phasor when you add V1 and V2? It is same as what? I mean, it is equal to what? Square root of mod V1 square. What do you mean by mod V1? It is the length of the phasor V1. It is the length of phasor V1. That is what? Mod V1. So square root of mod V1 square plus mod V2 square. What is mod V2? It is the length of this other phasor V2. So mod V1 is what? Length of phasor V1. Mod V2 is what? The length of phasor V2. So square root of mod V1 square plus mod V2 square plus 2 times mod V1 mod V2 and then cos theta. That's all. This is how you calculate the magnitude of the resultant phasor when you add these two phasors. Okay, so mod V1 plus V2 is what? Square root of mod V1 square plus mod V2 square plus 2 mod V1 V2 cos theta. I mean, you will either add two voltages or you will subtract two voltages. This is for the case of addition of two voltages, okay? You can also subtract, right? So what is mod of V1 minus V2? Everything will be same except that in front of the third term you would get a minus sign. So square root of mod V1 square plus mod V2 square minus 2 mod V1 V2 cos theta. Now you can consider a couple of special cases. First one being V1 and V2 are what? Perpendicular. V1 and V2 are what? Perpendicular. So what do you mean by V1 and V2 are perpendicular? The angle between the two phasors is what? 90 degrees. Angle between the two phasors is what? 90 degrees. If the angle between the two phasors is what? 90 degrees, then cos 90 degrees, would it not be 0? Cos 90 degrees, it would be 0, right? Yes. Then the entire third term would become 0. You will simply get square root of, I mean, it's like having a right triangle. If two phasors are what? Perpendicular, or the angle between two phasors is what? 90 degrees. It's like having two, perpendicular vectors, and then finding V1 plus V2 magnitude is same as what? Finding the length of the hypotenuse. Finding the length of the hypotenuse. So in this case, mod V1 plus or minus V2. So mod of V1 plus or minus V2 is equal to what? Square root of mod V1 square plus mod V2 squared. Okay. Now V1 and V2 are in phase. The second case is what? V1 and V2 are in phase. What do you mean by V1 and V2 are in phase? The angle between V1 and V2 is what? 0. That means both the phasors are pointing in same direction. Both the phasors are pointing in same direction. They can have different lengths, but angle is what? Same for both V1 and V2, and that is when we say V1 and V2 are in phase. Okay. So when I say V1 and V2 are in phase, then it means angle of V1 is same as what? Angle of V2. If angle of V1 is same as what? Angle of V2, then what is the angle between the two phasors? Angle between the two phasors is what? Phase difference, or the angle difference between the two phasors. Angles are equal. Then theta, will it not be 0 degrees? If theta is what? 0 degrees, again going back to this expression for mod of V1 plus or minus V2, cos 0 degrees, is it not 1? Cos 0 degrees is what? 1 when V1 and V2 are in phase. If cos 0 degrees is what? 1, will it not become square root of mod V1 square plus mod V2 square plus or minus 2 times mod V1 V2? So in this case, mod of V1 plus or minus V2 will be equal to what? Mod V1, mod V1 plus or minus mod V2. Mod V1 plus or minus V2. You understood? Yes. I mean, a square plus b square plus 2ab is what? A plus b whole square. Or a square plus b square minus 2ab is what? A minus b whole square. Same thing I've used here. So when the two phasors are in phase, when the two voltages are in phase, then the angle between the two phasors is what? Going to be 0, because both will point in what? Same direction. If you are adding those two, you can simply add the two lengths. If you are subtracting those two, then you should simply subtract the two lengths. Okay. And then we have another case where V1 and V2 are 180 degrees out of phase. You can also have a set of two phasors which are 180 degrees out of phase. V1 and V2 are 180 degrees out of phase. That means what? Both the phasors will point in what? Opposite direction. If one phasor is what? Pointing towards the right, the other phasor will exactly point towards the left. That is the meaning of V1 and V2 are 180 degrees out of phase. In other words, the angle between the two phasors is what? 180 degrees. So this means theta is what? 180 degrees. Angle between the two phasors is what? 180 degrees. If the angle between the two phasors is what? 180 degrees, then if the two phasors are what? Pointing in opposite direction, if you are adding the two phasors, then you have to subtract the smaller phasor from the longer, or the shorter phasor from the longer phasor. You understood? If theta is what? 180, then you know cos 180 degrees, it would be minus 1. So the point is what? Mod of V1 plus V2. Mod of V1 plus V2, it will be equal to what? Mod of V1 minus mod of V2. You understood? And this is when the two phasors are 180 degrees out of phase. Mod of V1 minus mod of V2. And mod of V1 minus V2. What is this mod of V1 minus V2? Just keep in mind that the two phasors are pointing in what? Opposite direction. Now if you subtract one from the other, then V1 minus V2, the resultant will become what? Much longer than both the individual phasors. Will it not become mod V1 plus mod V2? Yes or no? Mod of V1 minus V2, if the two phasors are 180 degrees out of phase. Let's say one phasor is what? Along the positive real axis, the other phasor is what? Along the negative real axis. And if you are subtracting this phasor from the other phasor which is in the positive real axis direction, first of all, minus V2, that means what? This phasor has to be reversed. Now both the phasors will point in what? Same direction. Yes, it's like adding two phasors which are pointing in same direction. When you add two phasors pointing in same direction, then you just have to add the lengths of the individual phasors. That's why mod of V1 minus V2 is what? Mod V1 plus mod V2. But everything should be visualized, you know, from the phasor diagram. So these are some basic things related to representation of phasor quantities on the complex plane so as to get the phasor diagram. Okay? But the most important results are what? These two. Whenever we have Vm cos omega t plus theta, it can be represented in phasor form as what? Vm angle theta. And when you have Im sin omega t plus phi, first you write Im angle phi, just like Vm angle theta previously. Now you write Im angle phi. Because the function is what? Sine, you just add this minus j. You understood? If it is cosine, you just leave it like that. So whatever be it, the moment you come across the sinusoidal current or voltage, first you write down amplitude followed by phase angle, Vm angle theta or Im angle phi. If it is cosine, leave it like that. If it is sine, you add this factor, that is what? Minus j. That is how you convert any time domain sinusoidal quantity into its corresponding phasor representation, because we will be doing the entire analysis in the phasor domain. In the end, we will go back to our time domain. You see, the given thing will be in time domain. Yes, the given voltage source value or the given current source value, it would be in what? Time domain. But we will do the analysis in phasor domain because it is much more convenient to do the analysis in phasor domain. Once we complete the analysis in phasor domain and find the required, voltage or current in the phasor domain, then we'll convert that phasor back into what? Time domain. So you should be very comfortable going from time domain to phasor domain, then doing the analysis in phasor domain, and then in the end converting that phasor result back into what? Time domain. Because ultimately we want to find various voltages and currents as what? Functions of time. But we'll do the analysis in phasor domain. So in the end we should again come back to what? Time domain. So you should know how to go from phasor time to phasor and then back to time. So there is some basic stuff related to what? Phasors. So phasor is what number? It's a complex number which will represent a sinusoidal current or voltage. Okay. So when we meet in the next session, we will solve some problems related to going from time domain to phasor domain, and also from phasor domain back to time domain, and then we will get started with actual science or steady state circuit analysis. Okay.